Okay, so good afternoon, everyone. I just wanted to do a quick video of some examples. You're fine. Of some examples on the slideshow, so I'll go through a few of those. I didn't get any specific questions through email of things that you wanted me to go through, so I'll just talk about a few of these and maybe glance at the actual homework assignment to see what we might need to clarify on there. I did see that someone's been working through the homework and very well, might I add, so good job to those of you who are able to get through this just by reading the book. But for the rest of us, I definitely want to offer some assistance. So, of course, reminder, we are talking about energy, and specifically for now, we're starting at kinetic energy. And remember, the kinetic energy, KE is how I represent that, is equal to 1/2 mv squared. And what that means is, of course, that the faster something's going or the more massive it is, the more energy that object has. Now, despite the fact that velocity itself is a vector, energy does not necessarily have a direction associated with it. Now, once we start talking about work will have a direction, but energy itself is directionless. So we're not going to associate that with a vector. But let's start off by looking at slide number 14 on the slideshow. And number 14 says a 30 kilogram box initially sliding at 5 meters per second on a rough surface is brought to rest by a 20 Newton force due to friction. And the question is, what distance does that box slide? Of course, when we're looking at a question, we always want to find what information is important in the question. And in this example, all of that information is going to be necessary, right? We need to know how much force is going to be applied to something, how massive it is, and maybe even what velocity it's going at first. Remember, if something's going to change velocity, that means it's accelerating, which of course means that some force must be applied to it. So we'll start off with the work energy theorem. It says that 1/2 mv squared is equal to 1/2 mv naught squared, so that's the initial. And of course, plus force times the change in distance. So using this setup, we will be able to solve this question. And all we have to do actually is just plug and chug. We know how fast it's going when it starts. That's 5 meters per second. And the problem says that it's brought to rest by the friction force. So its final velocity is going to be 0. So we'll just go ahead and input some values here. I'm going to write on my piece of paper 1/2 and then the mass, that's 30 kilograms. The final velocity is going to be 0. So everything on the left half of that equation ends up being 0. Equals 1/2, still the same mass, that's 30 kilograms, times the velocity initially that it's going, that's 5 meters per second squared, plus the force, and it says that the force is 20 newtons. So we'll put this here, times the change in position. And what we're looking for is that change in position. But wait a minute now, we've got some problems happening, right? We've got a force acting. We know that force is a vector, and also change in position is a vector, and velocity is a vector. So think about that force really quickly. Is the force that slows it down, is it going to be acting in the same direction or the opposite direction of the motion? Right, because if I added a force in the same direction, it should be accelerating in that same direction. Since the force is in the opposite direction, instead of putting plus F change in position, that F is going to be a negative F. So I'm going to write negative F change in position because it's a force in the opposite direction. So I'll show you what's on my paper here as soon as I write it down again. Oh, my pen's dying. It's alright, I got another one. Okay. So If you can see that, look in the circled part there. It says 0 equals 1/2 30 times 5 squared minus 20 change in position. And that's because the force is in the opposite direction of the velocity. So as you're working through these problems, you'll always want to think, is my force acting in the same direction, positive, or the opposite direction, negative, of my velocity? So that lets me know if it's slowing down or speeding up. Once we're aware of that, we can start solving it, no problem. You'll just subtract the 1/2 30 times 5 squared, and I'll go ahead and simplify it on the paper. You can go ahead and subtract that from both sides. Minus 15 times 25 equals negative 20 times the change in position. I'll go ahead and solve that. Just divide out the negative from both sides. Of course, you'll divide both sides by that 20. And once we finish doing the math, we end up with the change in position being equal to approximately 18.75 meters. So what this means is that our box that's moving at 5 meters per second, with friction acting at 20 newtons, it will slide for 18.75 meters before it comes to a rest. And of course the check mark's already on the slideshow, so you could probably see the answer anyway, but I just wanted to clarify how you ended up with 18.75 as opposed to like a negative 18.75. And the important part is just remembering, when you're looking at these, you'll compare the direction that my force is acting versus the direction of my velocity. Same direction, positive, opposite direction, negative, right? Okay. And the next slide just asks about a car that's slowing down, and it asks if the work is going to be positive or negative. And the way you know that is, once again, you'll just think about, is the force in the work, is it acting against the direction of velocity? If it's acting the same direction, positive, against, negative. Now, I know we haven't talked too much about work as of yet, but we're going to get deeper into it as we keep going. Slide number 16 has a 13 kilogram car slowing from 18 to 15 meters per second, and it gives you a distance of 30 meters. You'll solve this very similarly to the last one that you solved, except this time you're going to be looking for the force. So it's just plug and chug, right? You'll set up the work energy theorem, you'll input the values that you need, and then you'll solve for the answer. Once again, look at this car, it is slowing down. If it's slowing down, that means that the force being applied to it must be in the opposite direction of motion. That means that the force will be considered negative, or you can think of it as doing negative work because the work is acting against the direction of motion. And then you'll be able to see that your answer comes out to be about 2145 newtons, and of course that's already check mark on there. So just clarifying the direction of work. So on slide number 17, all this works great, right? We can find the energy of an object based on if it's moving or not, right? We can find out how much work is being done on an object based on how it acts against a direction of motion or how it acts against the force. However, what if the kinetic energy at the start of a situation is the same as the kinetic energy at the end of a situation? For instance, if I have a phone here and then I lift it up here, has work been done on it? Right? We really haven't clarified what work is, but we're going to get to a definition of it as we keep going through. So let's start looking at some different situations, which is going to, of course, require us introducing a different concept. And of course, on slide 19, it says that we have two observations. It says that I can do work and have no change in kinetic energy, which is weird, right? Because we consider work oftentimes as the change in kinetic energy. However, I can do work but still have the same amount of kinetic energy. So that means we're going to introduce a different concept, the concept of potential energy. So this is a different type of energy, and you'll find that there are different types of energy and they're all related. But potential energy is, people usually call it stored energy, but I don't really like that definition. I consider potential energy the ability to do stuff based on the presence of a force. I consider potential energy the ability to do stuff based on the presence of a force. Now that's going to be specifically for gravitational potential energy, which is what we'll be talking about. But if you start looking at other types of potential energy, that definition might not work as well. But potential energy is represented by a capital U, as you can see on slide 19. And we have two different ways of writing it. The one we'll work with mostly is the second one that says potential energy, U, equals mgh. That's potential energy equals the mass times the acceleration due to gravity times the height, or the distance away from some zero height. So assume that the ground is 0 and then something's 2 meters above the ground. The height would be 2. So with anything where you have a height, you have to define some 0, as you can see on the slideshow there. And as I always say, wherever your 0 is, it doesn't matter, pick a place, that's your 0, but that's where it is, right? Once you decide that the ground is 0, then for the rest of that problem, or anything that interacts with the objects in that problem, that 0 must be the same. So if I decide that my 0 is the table here, then the table's 0 at all times, right? Stick with it. I usually make the ground 0 unless there's some specific reason for me not to. Now, also, like I said, there is other method of writing, other way of writing potential energy where U equals F change in position. But we're not going to focus too much on that right now. We'll look more into that later and how that relates to something else that is equal to F change in position. So we're going to start seeing some connections here. Get excited about that. The first question there on slide 20 just says we have a 4 kilogram rock sitting on a 3 meter high ledge, and it asks you to find the potential energy. And of course, we'll just take the mass of the rock, 4 kilograms, multiply it by the acceleration of gravity, that's 9.8. Multiply that by the height of the ledge, that's 3 meters. And of course, that gives us approximately 117.6 joules. No big deal, right? mgh is your potential energy. So that's not too challenging, right? As long as you remember that. But we're going to start getting some relations here that make it slightly more challenging. But for now, mgh, no big deal. Okay, the next problem on here, on 21, slide 21, it says a box with a mass 5.8 kilograms is lifted from the garage floor and placed on a shelf. If the box gains 145 joules of potential energy, how high is the shelf? So this is the same type of setup, except we're solving for something different, right? U equals mgh. Except now, I have the mass of the box, that's 5.8. I always have the acceleration due to Earth's gravity, because we're going to be on Earth for all of the problems, unless it explicitly states we're somewhere else. So 9.8 meters per second squared, right? I don't know my height yet, so that's what we'll be solving for. I have my potential energy that's added, So 145 joules. Okay. Look in the circled part there, and you see that that H is what we're going to solve for. And we'll just use standard algebra there. Divide the 145 by 5.8 times 9.8. And that'll give us the H. And the H is approximately 2.5 meters. So this is all super straightforward. We're doing great. This is almost as hard as it gets. Not quite. We're going to have to start doing some combinations. But for now, hey, no problem. Okay, so the next slide, slide number 22, this is where it all starts coming together. This is what makes all of this important and possible. There's something called the law of conservation of energy. The law of conservation of energy. The law of conservation of energy says that energy can neither be created nor can it be destroyed. The law of conservation of energy says that energy can neither be created nor can it be destroyed. So what that means for our problems is that if an object starts with a certain amount of energy, it should end with a certain amount of energy. Now, of course, this is all conservation laws like this are in a closed system, meaning that the total energy in the system must remain the same, and sometimes we won't be looking at closed systems, but we will learn to know when systems are closed or not. But for right now, what this means for us and the problems that we'll be solving is that the sum of all energies is constant. The sum of all energies is constant, meaning all the energies before must equal all the energies after. And of course, that's also on the slideshow. And also remember that we can add or subtract energy from the system by doing work on it. But like I said, we will get to a point where we know what energy is being added, how it's being added, and where it's going, right? Since we still can't destroy it. Now, the PhET tutorial that you find on slide 23 is a really fun thing to play with, because as you look through it, what you'll notice is that there's a total amount of energy that the skater will start with, and even if it loses some kinetic energy, it will gain an amount of potential energy equal to the kinetic energy that it loses, and vice versa. And this is going to be key for everything that we're working on. Let's see, I think this video's been long enough. I want to start my next video, which will be up on Friday, working on slide number 24, throwing the stone up. Through this, we'll get to see how the conservation of energy helps us solve problems. Keep struggling through it. Remember, send me emails. Whenever you send me an email, I will address it in my videos. I'm going to try to keep my videos under 20 minutes because I know 20 minutes of listening to me talk is enough. I'm tired of hearing myself right now. But anyway, everybody get to work. Email me questions. Please email me questions, right? Because we have to get through this whole alternate learning style together, and I want you all to be successful. Remember, Khan Academy is a good resource if you want to look through it. For those of you who have used Check Study costs money, so I don't recommend it. But if you just got money laying around, might as well check out Check Study. Of course, your book is a good resource, even though it's a little dense. That is all I'm talking about for now. Look forward to my next video. I That's it for now. Thanks a lot, guys. You all stay safe out there.